All right. Where did we leave off?
The scale, the qualitative,
Alright.
type and scale.
All right. So what's qualitative data?
The one about attributes.
Yeah, it's all about attributes. It's really what it is. We're describing it with the attributes. All right. In that qualitative scale, we can have nominal or we can have ordinal data. So what's the difference between those two? What's the difference between nominal and
ordinal?
nominal and ordinal?
Yeah, ordinal is in a natural or implied order.
Okay.
So if something is ranked, something like that, ordinal, nominal, not necessary.
All right. So if there's some sort of natural or implied ordering, right, then that's ordinal. Hence the name order, ordinal. And then nominal doesn't have that natural or implied order. All right, so what is quantitative? What are the types of variables that we could see that are quantitative in nature?
You said quantitative?
Quantitative. What are quantitative variables?
Describing numeric.
Okay, numeric data. We have two different types of quantitative data, right? So what are those types of variables?
Continuous and discrete.
Okay, continuous and discrete. So what's the difference between those two?
Continuous variables, you take on any value. It's not set. So it's like 0 to 1 would be 1 point, whatever.
Yep. All right. So yeah, continuous can take any value. It's going to be infinite number of values, and that kind of reappears again when we look at distributions, when we do histograms and probability distributions. Because if it's a discrete variable, we can actually calculate probabilities fairly easily because they can only take on whole numbers. Probability of rolling a 7 on at a craps table, you can get those defined numbers. But if we deal with a continuous variable, I can ask you, well, what's the probability of getting a specific number? Well, it's going to be very, very small. So when we work with continuous, we have to change to look at area under curves, which we'll do. That's where our probabilities come into play. All right. So in those quantitative variables, they can be either interval or ratio scale. So what's the difference between those two?
The intervals are like any like they can range from negative to infinity.
Okay, yeah, so it could range from negative infinity to positive infinity, or between definite values. All right. What is it lacking?
A zero.
A true 0 point. So when we take ratios, they're not going to make sense. And I said that in some cases the ratio could make sense, but it doesn't make sense across all values, across all scales. So ratio scale has that truly defined 0 point. All right. So let's go over these variables. We want to know the type and the scale for all of these. So let's kind of go through it, and let's have someone give me the variable type of shirt for our variable shirt size. Qualitative. All right. So why'd you choose that?
Because it's a size, medium, or large.
Yeah.
It's not a number.
It's not a number. It's small, medium, large. Not really in between. All right. Nominal or ordinal?
Ordinal.
Okay, ordinal. It has some implied order. Yeah, small to large. So yeah, this is qualitative. What about zip code?
Will that still be qualitative?
Who says qualitative? Got some. Calvin, is that right? Yeah. Calvin. All right. So what's you say qualitative?
Yeah.
I agree. All right. Why is it qualitative?
Describing attribute of the very thing.
Yeah. Is there any sort of ordering to that? Yeah. Yeah. I mean, there's we've tried to order it, but I mean the ordering doesn't make sense. I mean, if you look at it, I mean, it's not like we go from northeast down all the way to southwest and the numbers keep increasing. I mean, yeah, some zip codes in the same area tend to be closely together, right? The 76901, 902, 903, 904, 9. I think it's
like 909 or something.
yeah, like that's about it. But for the most part, these are it's qualitative, it's a description, it's an attribute. We use numbers as the attribute, but there's really no ordering to that. So this is a qualitative variable, nominal scale. Distance between cities.
Quantitative question.
Yeah, quantitative, continuous, or discrete. Continuous, right? Nothing says we have to be a whole, in miles or half a mile. All right, is this interval or ratio? Definitely ratio. Can't have negatives. All right, and I think that's the thing. You have to ask yourself, can we have a negative or not? Okay. If we can't have a negative, chances are it's ratio. Chances are it's ratio. Standardized test scores. This includes like the MCAT, GRE, IQ. Qualitative or quantitative? Quantitative. All right. Is this continuous or discrete? I'd say
No,
probably.
it's a.
Well, most of these
Or
were-
is it rated in
definitely
a
can go on
proportion
forever.
style?
I'd say it's more discrete because we don't have like decimal points or anything. It's always whole numbers, and they kind of look at percentages. Now, tricky part is this interval or ratio? Is it?
Or thoughts you ask, is it? No.
So we said it's discrete, so it's still quantitative. Right? Discrete variables could be ratio or interval. So these standardized test scores are great examples of the interval scale. There really is no 0 point on these. IQ, you can think about, well, what's the lowest IQ? You come up with the person that people have found to have the lowest IQ, but there's really no 0 point on it. Standardized test scores tend to be just kind of arbitrary because they're scaled based on how many individuals took the test at that time. So even though the numbers kind of have a range of, let's say, what's that MCAT's range now? 0 to 140, 160, 150. Yeah, I don't know. They've changed. They've changed a lot. But it ends up, your score kind of depends on how well other people did during that time period. So these standardized test scores, I put them up here just to kind of emphasize when you look up, if you're confused about interval versus ratio scale, the classic example that they give is IQ. Say IQ is interval scale, and you just kind of have to wrap your brain around it. The other classic example is temperature. So Kelvin scale, is that ratio or interval?
Wouldn't it be ratio?
That's ratio because Kelvin actually measures movement. All right, that's what the Kelvin scale is measuring, molecular movement. All right, Celsius and Fahrenheit measures what they term as heat. All right, and those can go negatives, and thus our ratios just kind of have very little meaning to it. All right, leaves on a bush. Qualitative, quantitative.
Quantitative?
Definitely quantitative. Discrete or continuous? I would say it's discrete because we don't normally count half leaves. Either they have the leaf or they don't have the leaf, right? Ratio or interval?
Ratio.
Yep, ratio. You can have 0. 0 leaves on that. Letter grade.
Qualitative?
Okay, qualitative. Right? We use an attribute, which is letter. Right? Nominal or ordinal?
Or ordinal.
Ordinal, because we set up a ranking system. We've kind of artificially created that ranking. But what about percentage grade? So grade if we list it as a percent. Quantitative, continuous, or discrete? Continuous, so we can have infinite number between 0 and 100%. All right. Ratio or interval? Ratio. Yeah, we can have a 0. We can have a 0 there. So this is up here to kind of demonstrate that some things grade can be grade can be either qualitative or quantitative. Same thing could be like hair color. Right? Although we typically say hair color is a qualitative trait. If we change color to wavelength of light, we've just now changed it to a quantitative type of variable. All right, time to complete a task. Quantitative, continuous or discrete? Continuous. So a lot of times we say time to complete a task, we assign seconds or we assign minutes, but in reality, we can actually get all of those, milliseconds, and all of that stuff. All right, ratio of measurement variables. So the example I have here is surface area to volume ratios. Qualitative or quantitative? Quantitative. All right, continuous or discrete? Continuous. All right. Ratio or interval? Ooh.
You don't have a negative surface area.
Now, can we have a 0 in these? Trick question. Even though it has ratio in its name, this is actually interval scale. This is another aspect where, and it's kind of like with some of these standardized test scores, you can't have a 0 volume because then you're going to divide that entire ratio by 0. So 0 out of 0 is basically undefined. So we can get really close to that 0 point without actually getting to it. So that's another way to think about our interval. All right, so we have, go. All right, so kind of a summary for the scale, counts and frequency distributions. That could be, we can generate these counts of frequencies, tables for all of our scales, all of our variables. We can go through and count how many of our data points have a specific measurement, how many of our data points have a specific size. All right, mode and median, those statistics, so most common value and the 50% value can only be calculated for ordinal, interval, and ratio scale variables. Order is only known for ordinal, interval, and ratio, not for nominal. All right, quantifying the distances and adding, subtracting is only going to be applicable for our interval and ratio scales. Some people will try to do it with ordinal, right? So they'll try to take a difference in satisfaction values. You have to be really, really careful because a satisfaction value of 1 versus a satisfaction value of 2 could be a very different jump from going 2 to 3. All right, and then multiplying and dividing values, really only ratio has a true value. That's our ratio scale. So quick summary. All right, so with these variables, we're going to have a quiz where I'll list examples, and then you give me the variable type, so quantitative, qualitative, and I might ask for the quantitative, I'd normally ask either give me qualitative, discrete, or continuous, and then for the scale, it's going to be nominal, ordinal, interval, or ratio. So we'll have a quiz that has these. And I think the quiz is going to be online on Blackboard. So that accommodates any people that are watching video, watching from home or their dorm.
When is that?
I haven't made it yet,
Okay.
so sometime next week it'll go live.
Okay.
It'll go live next week. All right, so key points on variables. Just kind of as another review. Statistical tests mostly depend on the type and the number of variables that we're working on. I say mostly because it also comes down to the question that you're asking. All right, so the rest of it is like, well, do we want to compare means? Do we want to compare variances and so forth? All right, so if we have qualitative variable, we're typically restricted to analyzing frequencies. Are the frequencies the same? Maybe do the frequencies match what we observed at another time point? If we're working with quantitative variables, then we're going to be working with tests that allow us to compare measures of central tendency and measures of dispersion. All right? Scale of measure has very limited influence. So, qualitative versus quantitative, that was really where our big differences fall. Those are the ones we really have to focus on. If we deal with categorical versus ordinal or continuous versus discrete, those have very limited effect because, let's say the qualitative variables, most of the tests that you do with just a categorical or a nominal variable can also be applied to an ordinal variable. The test that you do use for continuous data is basically the same test that you would use for discrete data. All right, there's really very little difference. There is a point with categorical versus ordinal where we could do a different test that assesses direction. So is one better than the other? All right, so there are tests like that for the ordinal data, but by and large, if you do a goodness of fit test for a categorical variable, you can also do a goodness of fit test for ordinal data, no problem. And the same thing with continuous and discrete. Difference for continuous and discrete, though, comes with the display that you would use. All right, you want to choose a display that really emphasizes the underlying data. So you're not going to have a best fit line, or you're not going to connect your data points if you work with discrete data, because that line that connects the points implies that you can take on any value in between those points. You can't with discrete data. So you have to avoid things like that. Again, does it affect our ability to actually run a statistical test? No, it comes down to our presentation. What figure is best? And we'll talk about those. All right, any questions on our variables before we move on? If anyone watching has questions, you can type it into the chat. I will see it when I turn back and look at the computer screen. All right, accuracy and precision. These are two terms that we will use throughout the course. Accuracy and precision is all about how good we do at collecting our data. And that includes our sampling regime. So as we do statistics, as we do our data, we always want to be as accurate and as precise as we possibly can. Why? It's because when we are accurate and we are precise, we have a very small amount of sampling error associated with it. All right, so sampling error is all of the area. I'm going to have to move. Sampling error is all of that error that is associated with our data collection. All right, and sampling error is going to be the chance error. Anything that comes up, just through random chance itself. Some of this is due to us, our measuring device. Some of it is just due to randomness out in the environment. All right, so the scales. If you're measuring weight and you put something on a scale, today it might weigh, 1.5 grams. Tomorrow it might weigh 1.6 grams. There's error built into the scale. Right? And it's just, maybe it's a voltage thing with the scale itself. Who knows? Right? So what we want to do is try to minimize the errors as much as possible. We also want to eliminate bias. So bias is a systematic discrepancy associated with our data collection. All right. So we talked about making sure we have a random samples, and if we're doing, let's say, surveys here on campus, if we want a true random sample, we're going to have to sample students across all of campus, because students that made, whatever their major is, they tend to only visit the buildings where they take their majors classes. If we didn't, then what happens is we introduce bias, which is a systematic discrepancy. Going back to our scale example, to our balance example, maybe our scale always weighs low. That's a systematic bias. The scale over down at the blood donor center at Vitalant, I am 100% convinced it is biased high. All right. Honestly, I think it is biased high. So, bias and sampling error, what do they affect? Accuracy, how close we are to the true value, is affected by bias. All right, so if we have a measuring device that is biased, if we ourselves are biased, then we are going to influence our accuracy. So accuracy is the closeness of our sample values, our sample statistics, to the true value. All right. So a way to think about it is think about a bullseye and target practice. Okay. So we have a bullseye. We're always going for the middle. If we are accurate, we are going to be around the bullseye. If we are not accurate, we're going to be off the bullseye. All right, we're biased. We're systematically low and to the right. Precision is affected by our sampling error. Precision is the repeatability of our data collection. All right. On our graph, precision refers to the spread of our data points. In this case, we are highly precise. So that group, this is precise, and we are accurate. This group, this is precise and not accurate. Not accurate. So we're off the target, yet we still have a very tight group. What happens if we're not precise? Not precise, we're going to be all over the place. Some people would say something like that is not accurate. I would argue otherwise. Because if we look at our grouping, our grouping's very wide. All right, we're not very precise. But if we look at the average value of all of our groups, we are smack dab in the middle. We're accurate. But we're not precise. Or we can be way out over here. Again, really scattered in our data. These are neither accurate nor precise. All right. So we can be very unprecise with our measurements, but when we take our averages, when we take our means, when we take our medians, it could put us exactly on our true value, where we should be. All right. So the precision doesn't really affect our accuracy, just like our accuracy doesn't affect our precision. All right. These are two different concepts. Accuracy is affected by bias in our data collection. That bias is going to move us off our target. Precision is affected by the sampling error. The more sampling error we have, the more scattered our data points are going to be, the larger the variance. In terms of our measures of central tendency, which is kind of where we typically focus on, which is a balance point type deal, and dispersion, which is the spread of the data, precision affects that dispersion, accuracy affects our central tendency. All right. So of all of our variables that we work with, these continuous variables are going to be the most difficult to be precise. And they're the most difficult ones to increase precision because of rounding. Because we are going to be rounding these values. We can't work with 20 decimal points. We're going to round them and work with 1 or 2 or 3 decimal points. And that increases, or that reduces our precision. All right, so I do have this figure, kind of just what I diagrammed to illustrate the relationships. They're independent of each other. You can be accurate, but not precise. And again, you're accurate means our center point is right on target. Okay. Precision is spread of our data. We strive for accuracy and precision. That's what we strive for. Any questions on accuracy and precision? All right, rounding. So we work with continuous data. I said one of the hard parts of being precise is through rounding. All right, so how do we round? Or why do we round? We round to make it easier to work with our data. All right, and in a lot of cases, we're rounding because our instrument that we're using to measure our device is imprecise. It only has a certain level of precision tied to it. All right, you look at a ruler. All right, it's got centimeters, it's got millimeters on it. That's about it. All right, its precision goes down to millimeters. It doesn't go down to 0.1 millimeters or 0.001 millimeters. It's limited. Scales, balances, have different precisions. The balance that I have upstairs has 1/1000th of a gram, I believe. That's its precision. And actually, it says, I think, plus or minus 5/1000th of a gram. So it's within 0.5. Everything's going to have differences in precision. So what we're going to do is look at that precision value, and then we'll round our value to try to make numbers that are easier to work with. When we round these values, though, we have to recognize that they actually have something called an implied limit. The implied limit is the range of measurements where that actual true value lies. So if we measure something on the scale and it returns a value of 2 grams, is it exactly 2 grams? No. That scale is giving us a rounded value. And that rounded value means that the true value is going to be someplace between 2 points. Now, where are those points? Those 2 points are basically the points that are going to be rounded down or up to that value 2. So for us, it's going to fall anywhere between 1.5 grams and 2.4 grams. Because those are the values that would round it to. All right. So with our implied limits, we always look at wherever that last digit we rounded, and then we always go one more digit to make our implied limits. All right. When we do these roundings, when we round our own data, we are actually going for a specific target. If you're in chemistry, they always say significant digits. There's a reason. Because if you do significant digits correctly, then we're going to have between 30 and 300 steps between the largest and the highest value in our data set. That's our target. All right. In most cases, if you just do standard rounding, you hit this. You get this. But sometimes your data points are just so, precision of the instrument stinks so much that you basically have 2 values. 2 grams and 3 grams. That's it. Well, you can't tell much from that. In order to improve, you're going to have to find another balance or another scale that has higher precision so that we can aim for this 30 to 300 steps. All right. So we want to have enough precision that allows for data analysis, but we don't want so much precision that instrument error starts to become the main difference. And I do put it up here. Experience and practice in rounding just kind of gives you an idea of where we should round. Where should we round? All right, so how do we round? Hopefully this is review. Hopefully you know how to round. I know my daughters were talking about rounding last year. Let's see, she was in 5th grade. I believe that was her. And I said, oh, that's funny because I just talked about rounding in my stats class. She's like, really? I'm like, yeah, we're still going over rounding, even in college. So how do we round? Basically, we look at our target digit. We want to know where we want to round, and then we go to that next digit. So just going to use some letters in place of our numbers. All right. Let's say our number is AB, period, C, D, E, and F. All right. We want to round here. That's where we want to round. And thus, we go to our next digit, E, and that tells us if we're going to round this digit up or keep it the same. So, the rules that we're going to go by is if this last digit is less than 5, not less than or equal to, if this is less than 5, then we're going to leave the number alone. If this digit is greater than 5, not greater than or equal to, but just greater than 5, then we're going to round this number up. Right? What happens if this number is exactly 5? Then we're going to have to look at the next digit, so the one next to that 5. If this digit is non-zero, then that means that this isn't just 5, this is a little bit larger than 5. And therefore, we're going to round this up. If this next digit is 0 or there's nothing after it, so it's just we end at 5, then what we're going to assume is that it is exactly 5 and we're going to leave D alone. We're going to leave that alone. All right? We're going to do that because this is what R does. So there is a round function in R and we'll use it. We'll introduce it. All right? So we're going to do what R does. Problem with this is that we start to introduce a little bit of bias in our numbers. All right? We start to introduce a little bit of bias in the numbers because we're going to start leaving this number alone a little bit too frequently. So we're going to bias our estimates of means a little bit low than the true value. So some textbooks actually have another rule about what to do, and it says that if this number is 5 and it's either 0 or nothing after it, then if this target digit is odd, we round it up. If it's even, we leave it the same. So that way we kind of balance out times you increase it and the times you decrease it. It's meant to eliminate bias. Are we going to do this? No, not at all. We're not going to do any of this part. We're just going to look at that digit. If it's greater than 5, we round up. If it's less than 5, we leave it alone. If it's greater than 5, that means also if it's 5, we look after it. If there's any number that is larger than 0, we round up. If it's 0 or nothing after it, we leave it alone. Easy? Easy? All right, so let's go through this rounding practice. Right? And I think the quiz will include variable types and also this rounding. So it'll be doing it by hand. This is a little bit digits, digits column. I've had quite a people ask, well, is this numeric digits? Is this significant digits? So on all future quizzes and exams, I will actually tell you where to round. So here it says round to 2 digits. I'm going to say round to the ones place. All right. So how do we round? Our number is 13.5. 13.35. 13.35. All right. We want to round there. So I might bold it, or I might underline it and say, we want to round here. What's our rounded number? 13. That's our rounded number. All right. Next one, 0.9551. We want to go to 2 digits. I'm going to say we want to round there. What's our number?
0.92.
Yep. So we want to round to that digit. We go to the next one. It's a 5. There is something after it. So we're slightly above 5, which means we're going to round up. 0.0113. We're going to go to that digit. Yeah. So you've done this before. Hopefully it's easy. All right. Now, what we haven't done is talked about these implied ranges. All right. So this rounded number means that our value, it doesn't mean that our value is exactly 13. It means that our value is someplace within that range. Which range is it? That's our implied limits. Zoom, open this, make this a little bit larger. All right, so what is our implied range?
Yeah.
Yeah, so let's say, what's our implied range of 13? Yep, so 12.5 to 13.4. Now the implied range, I'm just going to keep it simple because the only thing this is doing is just driving home this point that when we round, even with our instruments, doesn't mean that it's exactly at that value, that it can take on a range of values. All right, and our implied limits, this limits can have an effect on our error, and error can get magnified as we start to transform our data. All right, so yeah, I'm not going to say 12.51 to 13.4. I'm just going to say it's 12.5 to 13.4. Leave it at that. All right. What about 0.96? What are the implied limits for that?
0.0915.
Yep. 0.955 to 0.961. What about 0.011? Yep. So it's getting a little bit trickier. All right, because we had to drop that 1 down to a 0. Right? All right, so go ahead and do the same. Round these numbers that are up here, the last 3, and get the implied limits. You don't need to know the rule. It's part of learning. So what we are looking for is, for this one, we're going to round to the 3. So 0.1953, we're going to round to that 3. For this one, we're going to round where that 9 is. That's our target digit. And then for the 5, we're going to target the 8. All right, so round it, get the implied limits, and then we'll go over. Move this up a little bit. Now, people don't get motion sickness. Moves. That's better. Those are our numbers. right, you guys done? All right, let's go over this. First number, what's our rounded number? Yeah, 0.1953. Go to the next digit, it's less than 5, we leave it alone. All right, what's our implied limits of this number? .19525 up to 0.19534. What about this one? Yeah, nothing's after it. So our target digit was a 9. We look to the next one. It's a 5. So we look after it. There's nothing after it. So we assume that that's a 5 and we leave our digit alone. This is one of those cases where R is going to give us this number, this same number. All right, what's the implied limits? Hopefully it's 885, right? Up to 0.27894. Now you see what happens here. Our implied limits didn't capture this value. And that's something we just kind of have to recognize, right? Because 5 is that cutoff, all right? So the reality is that this kind of goes up to like 0.50, 278,950 repeating, all right? But for us, we're just going to keep it simple and go 5 up to 4. We're going to keep it simple like that. What about this last number? Eight zero, right? All right. And if we do our implied limits, and we kind of have the same type of issue again. We didn't capture it. We didn't capture it, but again, there's nothing after that 5, so we just leave our value alone. We're not going to round it up.
Will that mess with our data at all if it doesn't match?
Not really, because our true implied limits, you have to think, these are continuous numbers. This goes all the way up to this, 125,985.0 repeating out. All right, that's our true implied limits, but for us, we're keeping it simple to say it goes up to 4.
Oh, okay.
All right, goes up to 4. All right, so what we're gonna do is stop here. I don't think I have like a homework practice. So I do have the numbers. So that's kind of what we went through. All right. What we're gonna do on Monday is we're gonna talk about rounding in R. So I think what we'll do is have I'll get the quiz together and it'll probably get posted on Monday, either sometime over the weekend or on Monday, and you'll have until I think Wednesday to take it, because I know that our second quiz, or actually I should say our homework assignments, gonna work with R to do some of this rounding and forwards. So we're not done with rounding yet. We're gonna see how to do it in R, and you'll see that everything that we did by hand, R is gonna give us the same answers. All right, so we are done. Enjoy the weekend. Stay safe, hopefully. All right. Cody.